Welcome to this deep dive into the heart of every electric vehicle, the battery system. I'm excited to guide you through the technologies that power the future of mobility. Whether you're an EV enthusiast, student, or engineer, this session will help you understand the science, performance, and promise of batteries like Li-ion, LFP, NMC, sodium-ion, and solid-state. Let's get started on this electrifying journey toward a cleaner, smarter, and more sustainable future. Electricity is the driving force behind electric vehicles, and to understand how EV batteries work, it helps to start with the basics. Current is the flow of electric charge through a conductor like a wire. You can think of it like water flowing through a pipe. The more current, the more electricity is moving. This is measured in amperes, A. On the other hand, voltage is the pressure that pushes this current through the circuit. Imagine it like water pressure. Higher voltage pushes more current. Voltage is measured in volts, V. For example, a 12 volts battery pushes current more strongly than a 3.7 volts one. In electrical systems, every device or wire has a current rating, which tells us the maximum current it can safely handle. Exceeding this limit can cause overheating or even failure of the device. For example, a battery with a 10 amps current rating should not be used to power devices that draw more than 10 amps continuously. Now let's look inside a battery. A battery has three main parts: the anode, cathode, and electrolyte. The anode is the negative terminal where electrons come out during discharge. The cathode is the positive terminal where electrons flow in. Between them is the electrolyte, a material, either liquid, gel, or solid, that allows the movement of ions between the anode and cathode. This movement of ions and electrons generates electricity when the battery is discharging and stores electricity when charging. Another important concept in batteries is the C rate, or C rating. It tells us how quickly a battery can be charged or discharged safely. A 1C rating means the battery can be fully charged or discharged in 1 hour. So, a 32Ah battery at 1C can safely deliver 32 amps. At 2C, it can deliver 64 amps. Charging or discharging above the rated C level can lead to overheating and reduce battery life. Each battery cell has specific voltage characteristics. The nominal voltage is the average voltage during normal operation. The full charge voltage is the highest voltage a battery reaches when fully charged, and the deep discharge voltage is the lowest safe voltage before the battery gets permanently damaged. For example, a typical lithium-ion cell has a nominal voltage of 3.7 volts, full charge voltage of 4.2 volts, and deep discharge voltage of around 2.5 volts. Battery life is also affected by how often it is charged and discharged, known as cycle life. One charge and one discharge together make up one cycle. The number of cycles a battery can handle before its capacity drops significantly depends heavily on the temperature. At room temperature, around 15 degrees Celsius to 25 degrees Celsius, batteries last longer, often 1,000 to 3,000 plus cycles. But if the battery is used in extremely cold, below 0 degrees Celsius, or hot, above 40 degrees Celsius, conditions, it degrades faster and the cycle life shortens. In summary, understanding electric vehicle batteries involves learning about current, voltage, battery structure, safe charge rates, C rate, voltage limits, and how temperature affects lifespan. This knowledge is essential not just for using EVs efficiently, but also for maintaining battery health and safety over time. Here's a detailed explanation of different types of electric vehicle, EV, battery systems, including their chemistry, cell characteristics, charging types, voltage ratings, discharge behavior, and cycle life performance across temperatures. How an EV battery cell works. A battery cell is the smallest building block of a battery pack. Inside the cell, chemical energy is converted into electrical energy through a process called electrochemical reaction. Each cell has, during discharging, when EV is running, and during charging. 1. Lithium-ion, Li-ion, batteries. Lithium-ion batteries are the most widely used type in electric vehicles. These batteries use graphite anodes and lithium metal oxide cathodes, like NMC, NCA, or LCO. They are known for high energy density, relatively lightweight, and good cycle life. Nominal voltage, approximately 3.6 volts 3.7 volts per cell, fully charged voltage, 4.2 volts, deep discharge voltage, 2.5 volts to 3 volts. Recommended cutoff is approximately 3 volts, C rating, charge, discharge, 0.5 C1C charging, up to 2 C discharge depending on cell quality. Cycle life, 800–1500 cycles at 25 degrees Celsius. Temperature impact. Performance drops below 10 degrees Celsius and degrades faster above 45 degrees Celsius. Optimal performance between 15 degrees Celsius to 35 degrees Celsius. 2. Lithium iron phosphate, LFP. LFP batteries are a subtype of lithium-ion batteries, but offer better thermal stability, longer cycle life, and safer operation at high temperatures. However, their energy density is lower than NMC cells, making them bulkier. Nominal voltage, approximately 3.2 volts per cell, fully charged voltage, 3.65 volts, deep discharge voltage, 2 volts, cutoff generally at 2.5 volts. C rating, 1C to 2C charging, up to 3C or more discharge, cycle life, 2000 to 4000 plus cycles at 25 degrees Celsius. 3. Lithium nickel manganese cobalt oxide, NMC. NMC batteries are a type of lithium-ion battery and are popular for their balanced energy density, power output, and safety. Nominal voltage, 3.6 volts 3.7 volts, fully charged voltage, 4.2 volts, deep discharge voltage, approximately 3 volts, C rating, typically 0.5 C1C charge, 1 C2C discharge. Cycle life, 1000 to 2000 cycles at 25 degrees C. Temperature impact, works well between 10 degrees Celsius to 40 degrees Celsius. Performance drops sharply in cold. They are widely used in passenger EVs due to compactness and good all-round performance. 4. Sodium-ion batteries. Sodium-ion batteries are emerging as a sustainable and low-cost alternative to lithium-based systems. Nominal voltage, 2.3 volts 3 volts per cell fully charged voltage, approximately 3.2 volts deep discharge voltage, approximately 2 volts C rating, 0.5 C charge, 1 C discharge, still improving, cycle life, 1000 to 1500 cycles, newer versions aim for 2000 plus. Though still under development for large-scale EV use, they offer advantages in terms of resource availability and performance at lower temperatures. 5. Solid-state batteries, SSB. Solid-state batteries replace liquid electrolytes with solid ones, improving energy density, safety, and cycle life. Nominal voltage, approximately 3.7 volts 4 volts, depends on chemistry. Fully charged voltage, 4.2 volts or more deep discharge voltage, approximately 2.5 volts 3 volts. C rating, expected to be 1C-3C.IN. Future design cycle life, estimated 2500, 5000 plus cycles. Temperature impact, performs well across wider temp ranges, less risk of thermal runaway. Still under research, they are seen as the next generation EV battery technology, expected to revolutionize range and safety. Conclusion, temperature and lifespan summary from cell to battery pack, step by step. To power an electric vehicle, a single cell isn't enough. So, we combine many cells to make a battery pack. Here's how it's done in simple steps. Cells grouped into modules. Cells are first arranged into modules. Like small building blocks, cells are connected in series to increase voltage, and in parallel to increase capacity, too. Modules combined into battery pack. The pack includes safety features like BMS, Battery Management System. It monitors temperature, voltage, and current for safety and performance. Cooling systems, to manage heat during charging, discharging. Fuses and protectors, for over-voltage or short-circuit protection. Battery pack installed in the vehicle. The battery pack is mounted safely under the floor or inside the frame of the EV. It powers the electric motor, lights, controller, and other electronics. 1. Lithium-ion, Li-ion, batteries working. Uses a graphite anode and a lithium metal oxide cathode. Lithium ions move between these electrodes during charging, discharging. High energy density and common in many electric scooters and cars. Example pack. Each cell equals 3.7 volt, 2.5 R, 100 cells in series equals 370 volts. 2 sets in parallel equals 5 R, total energy equals 370 volts times 5 Ah equals 1.85 kilowatt hours. Used in most electric scooters, e-bikes, and EV cars like Tata Nexon EV, with NMC chemistry. 2. Lithium iron phosphate, LFP, batteries. Working. Safer and more stable with iron phosphate cathode. Longer cycle life and good thermal stability. Slightly heavier and larger due to lower energy density. Example pack. Each cell equals 3.2 volts, 3 Ah, 100 cells in series equals 320 volts. 3 sets in parallel equals 9 R, total energy equals 320 volts times 9 R equals 2.88 kilowatt hours. Used in electric commercial vehicles, buses, and budget EVs like the Tata Tiago EV base model. 3. Lithium nickel manganese cobalt oxide, NMC. Working, uses a mix of nickel, manganese, and cobalt in the cathode. Provides a good balance between power and safety. High energy density, but costlier and needs better cooling. Example pack. Each cell equals 3.7 volts, 2.8 Ah, 96 cells in series equals 355.2 volts. 2 sets in parallel equals 5.6 Ah, total equals 355.2 volts times 5.6 Ah equals approximately 2.0 kilowatt hours. Used in mid-range electric cars and two-wheelers. 4. Sodium-ion batteries. Working, similar to lithium-ion, but uses sodium ions. Less energy dense but better cold temperature performance. More eco-friendly and lower cost due to abundant raw materials. Example pack. Each cell equals 2.8 volts. 4 Ah110 cells in series equals 308 volts. 3 sets in parallel equals 12 Ah, total equals 308 volts times 12 Ah equals 3.7 kilowatt hours. Used in upcoming budget EVs and backup storage systems, emerging tech, already tested in some Chinese EVs like Jack and BYD. 5. Solid-state batteries. Working, uses solid electrolytes instead of liquid. Very high energy density, ultra safe, and long life. Still under development. Ideal for future EVs. Example pack. Future expectation. Solid-state batteries replace liquid electrolytes with solid ones. Improving energy density, safety, and cycle life depends on chemistry. Used in future, Toyota, Samsung, and other OEMs are testing in concept EVs and premium electric cars. Comparison quick view. Thank you for joining us on this journey through the world of EV battery systems. We hope this session helped you gain clarity on how these technologies work, their strengths, and their future potential. As we drive into a greener tomorrow, knowledge will be the real power behind our progress. Stay curious, stay charged, and keep moving forward with electric energy. Powered by SARIPUDI EV, the future of mobility, with you.